When we create machine learning systems, some applications fit really well with a simple rule-based approach. The machine learning algorithm can discover the principles governing the task and express the results simply. That's what we focused on last time, and it can be a powerful approach. But for other problems, simple if-then logical rules just don't seem to be the right representation for capturing what's needed to solve a task. We need a different building block for the rules. An analogy I like to use for understanding different approaches to building rules is Legos versus modeling clay. You can build a model out of either. Decision trees are like Lego models. They are made up of interlocking pieces that come in a variety of types. Each piece is one Lego brick or one attribute split in a decision tree. By contrast, with modeling clay, you can build a model down to any size and smoothness you want. In this lesson, we'll talk about neural networks, which are constructed out of parts that allow smoothness, more like modeling clay. Neural networks have variables that can be set to any possible numeric value, allowing fine-scale control over their behavior. In practice, this fine-scale control often works like the sliders on a mixing board that sound engineers use. It's not just on-off or the counting numbers 1, 2, 3 up to 10, it's also everything in between. So thanks to this very fine-scale control, neural networks give us an approach to machine learning that can build much more complicated systems of rules using very low-level inputs such as sound or images. These more complicated systems of rules would be hard for humans to derive explicitly or even fully understand. Humans don't think of pictures in terms of pixels or sounds in terms of sound waves. And yet, focusing on these low-level features is what makes it possible for machines to solve perceptual problems on our behalf. Neural networks allow machines to do the hard work of identifying higher-level patterns from lower-level inputs. For example, words from acoustic signals, people from images of their faces, letters from handwritten stroke information, and breeds of dogs from photographs. Deep learning, which has exploded in impact and popularity since 2015, is just an approach to building and training neural networks with many layers. To see why something like neural networks are needed, let's consider the problem of recognizing human faces. It's one of many hard problems in AI that people are very good at, despite being unaware of what we're doing when we're solving these problems. And because we don't know how we do it, it's really hard to verbalize an explicit rule that a machine could use to solve the same task. If we try to get machines to recognize a face via simple rules, the rules might look like this. If brown eyes, curly hair, energetic, pleasant, smart but approachable, larger than average nose, then it's Michael. This approach works in some cases. The person in this photo doesn't have brown eyes or curly hair, and the nose is small. It's not me. It turns out it's Emma Stone, star of many major motion pictures, but no machine learning courses. Yet. What does the rule do with this person? Well, it matches on all the features, so the rule would classify this person as me. But no, it's not me. Returning to the fundamental recipe of machine learning, a machine learning approach requires a representational space, a loss function, and an optimization procedure for selecting low-loss rules. Short, human-understandable rules don't seem to be a good fit for the problem of recognizing faces. Although it's conceivable that the right set of 33 features would be sufficient for uniquely identifying all 8 billion faces on Earth, no one has figured out which features those would need to be. There's not a clean, logical hierarchy. So to deal with low-level perceptual information like we find in facial images, we're going to need something more powerful, allowing many subtle distinctions to be made. Instead of a rule in any simple sense, we're going to want something more like an entire program. To generate such a program capable of so many subtle distinctions, we need a way for machine learning to optimize over possible programs. How could we optimize over programs? That's really hard. Even if we start off with a program that's pretty good, improving that program is very similar to the problem of debugging, and debugging is not a task we know how to automate, which is why it's really hard even for experienced human programmers. The fundamental insight of neural networks is that we can represent very big, very general programs capable of making many subtle distinctions, yet in a form that is simple and regular, and therefore amenable to systematic optimization. A neural network representation consists of units, weighted connections between the units, and an activation function in each unit. The original metaphor for neural networks is that the units are like neurons, where each unit is getting activated to differing degrees. These activations determine what values will be propagated along the connections. In this diagram of a neural network, the hidden units are represented by yellow circles, the output units by green circles, and the connections between the units represented by light blue lines. In this picture, the connections are propagating information from the input on the left to the category of the image on the right. The network is taking in images and distinguishing which images are cats and which are dogs. The input units correspond to pixels in the image being classified. The output units are the classes to be recognized, and the hidden units carry out useful intermediate calculations. For instance, if we were designing one of these networks by hand to distinguish cats from dogs, we might assign a specific hidden unit to a specific quantity we'd want to compute, like the degree of pointiness of the ears. That's a hard thing to define. But because we can have many, many hidden units, we can divide up the recognition of pointiness into smaller computational pieces. We can recombine those pieces across the units later to complete the overall recognition at the output layer. Here's how computation proceeds in this kind of network. Each unit holds a single real number. Following the nervous system metaphor, we call each unit's number its activation, how excited it is. Some of these units hold the input the network is processing. For image recognition, there would be 3 input units for each pixel of the image. One for the amount of red in that pixel, one for the amount of blue in that pixel, and one for the amount of green in that pixel. Some units hold the output the network produces. If the network is distinguishing pictures of cats from pictures of dogs, there might be 2 such units. One specifies the degree to which the network believes the input image is a cat, and the other specifies the degree to which the network believes the input image is a dog. The rest of the units are called hidden units, and they carry out intermediate computations. For a problem like object recognition, there could be hundreds or thousands or even millions of hidden units. Aside from the input units, whose values are set by the input, all of the other units perform very simple calculations. Each unit has connections from some subset of the other units. The connection patterns are acyclic. No unit's value can be based, even indirectly, on its own value. Each connection has an associated weight, which is just another numerical value. The activation of a unit is obtained by taking the weighted sum of the activations of all the units that connect to it. This weighted sum is then transformed into an activation using, appropriately enough, the unit's activation function. So to process an input, the activation for each unit is computed based on the activations of the units that connect to it. The activations propagate through the network from input to output and then stop. Since there are no loops in the connectivity pattern, this propagation is guaranteed to end quickly. You can think of each unit as carrying out a simple rule-like calculation. By connecting the units into a network, the units can work together to produce the complicated computations we need for solving hard perceptual problems. When the chain of propagation is relatively short, like 2 or 3, we just call the network a neural network. When the chain is longer, like 20 or 60, we call it a deep neural network. There's no mathematical distinction that defines a sharp boundary. Even 4 layers seemed pretty deep early on. The adjective deep just reminds us that we're talking about the more recent approaches to neural networks that began to become popular around 2015. Now that we have a pretty good idea of the overall flow of information in a neural network, let's zoom in to a single unit to see what it does. We can write X sub I to stand for the activation of each upstream unit, and W sub ij to be the weight on the connection from unit I to the unit j we're talking about. Then the summation over I for X sub I times W sub ij gives us a weighted sum of those activations for this one unit. I'll call that sum S. The weighted sum gets pushed through an activation function, written lowercase sigma. That activation gets sent downstream to the next layer of the units that it connects to. And just like an architectural blueprint gives information about the rooms of a building and how they are connected and information about their construction, neural networks also have an architecture. A neural network's architecture specifies the number of units and how they are connected. It tells us whether any weights are reused in different parts of the network. And it tells us what activation functions are used in each unit. Together, the components of the architecture define the representational space used for learning. Often, the units are organized into layers, with the connections to units in one layer only coming from units in the immediately previous layer. Some popular activation functions are linear, sigmoid, and ReLU. Let's take a closer look at these functions. All produce more activation given a larger weighted sum as its input. The linear activation function just returns the weighted sum coming into the unit as the activation for the unit. It has the form sigma of s is just equal to s. This activation function is simple and easy to work with. It's been shown that there are ways for you to train the weights of networks consisting solely of linear activation functions so that you're guaranteed to perfectly minimize loss. That's great. But linear activation functions have the unfortunate property that using them in all the hidden units of a network renders those units irrelevant. That is, any neural network with hidden units that only use linear activation functions can be transformed into a neural network with no hidden units at all. In 1969, Minsky and Papert published a book called Perceptrons, referring to a class of neural networks studied in the 1950s that were able to carry out simple recognition tasks. Minsky and Papert pointed out that these simple neural networks could not be used to represent some important problems. A simple example of such an unrepresentable function is one that maps temperature to comfort. As temperature increases, comfort rises. But once the temperature gets too high, comfort falls again. This up-down pattern cannot be captured using purely linear activation functions. Clearly, we'll need some nonlinearity for our network to be applicable to general problems. The sigmoid activation function provides a very simple kind of nonlinearity. Here, the sigmoid of the weighted sum s has the form 1 over 1 plus e to the negative s. The function moves smoothly from near zero activation to activation near 1 as the weighted sum goes from very negative to very positive. The sigmoid activation function is powerful enough that using it in a sufficiently big neural network makes it possible to approximate any function, which is a neat trick. A drawback is that sigmoid can be a little computationally expensive to use. Each time activation flows through a unit with a sigmoid activation, the computer needs to calculate the transcendental number e raised to some power. If there are hundreds or thousands of units making up the network, and we need to process millions or billions of instances through that network, the cost of computing the e exponential really starts to add up. One of the innovations that helped ramp up the deep learning revolution is the introduction of another activation function in the year 2000 called ReLU. It's a fantastic compromise between the simplicity of the linear function and the nonlinearity of the sigmoid function. The ReLU activation function has the form sigma of the weighted sum s is equal to s if s is greater than 0, and 0 otherwise. The name ReLU is a shortening of rectified linear unit. The linear unit part of the name comes from the fact that this activation function is just the linear activation function for positive inputs. But it is thresholded, so the output value cannot go below 0. That's the rectifying part. ReLUs are the most common activation function used in deep neural networks today. They are blazingly fast on the graphics processing units, or GPUs, used for training big networks. And they have just enough non-linearity, the little bend at 0, to render hidden units relevant again, letting them capture complex computations. Okay, so a neural network's architecture is the number of units, the connections between the units, and the activation functions those units use. Within this general framework, researchers have identified certain architectural patterns that seem to be very well suited to solving specific problems. There are common architectures for problems in natural language processing. Others are common in speech recognition. But the same architecture can carry out very different computations. A network that takes as input videos of faces could be trained to predict a person's emotional state, happy, sad, angry. Or those same networks using those same video inputs could be trained to predict what sounds people are making with their mouths. Ooh. What differs in these two cases are the settings of the weights. Since the weights can take on many possible values, network weights are sometimes called parameters. Training a neural network is the process of finding settings for these weight values that allow the network to compute the difference between cats and dogs or whatever the problem at hand is. You can also think of setting the weights as programming the network. We can take the view of a deep neural network as a kind of straight-through program, with no looping back and no forking with if-then statements. Each unit can be thought of as a single assignment statement in the program, where a variable's value is computed and then made available for future computations. So let's look at a single assignment statement from such a program. When we are defining the value of the variable on line j, call it x sub j, we multiply the value computed before it on line I by the weight wij between them. That is, we're taking the value of a variable from a previous line of the program and multiplying it by wij. Then we sum things up for all of the values of I, all of the previously defined variables. For conceptual simplicity, I'm allowing connections to all of the previous lines, although some of these would be removed from the sum if the corresponding units aren't connected. Next, we threshold the sum at 0, meaning we bump up the value so it's not negative. That's what the ReLU activation rule requires. The result is assigned to x sub j, and we can move on to the next variable. We assume some set of values is given as the input, like x sub 0 through x sub k minus 1 for some k. Those k values might be the numbers representing the brightness of each of the k pixels of an image. A 224 by 224 image with 3 color values per pixel means k equals over 150,000 values given to us in the input. Then, the rest of the program consists of a sequence of nearly identical assignment statements. Each line assigns its own variable using its own weights. The number for the first line comes from the size of the input, which was 150,528 values. The number for the last line comes from adding the number of inputs plus the number of units in the network's architecture. As you can see, the program itself is actually very boring. The only thing interesting about it is the weights, those W values. Setting those weights to different values gives us different programs, different computations on the input. And there are two powerful properties I want to point out about the structure of this boring program: universality and learnability. We'll look at each of these in turn. First, the structure is universal. Even though this program structure is simple and regular, it can represent just about any computation. That's in spite of the fact that there are no if statements and there are no loops. The only mathematical functions are sum and max. There's a formal logical argument that shows that we can convert almost any program piece by piece to a program that does the same computation but has this straight-through program form. To be clear, it's not quite any program. The lack of loops means we can only convert programs where there is a bound on the number of times a loop gets executed. So we can't convert a sorting program that handles lists of unbounded size, but we can convert a program that sorts lists up to any given fixed size. There are also some mathematical functions that we cannot compute precisely. For example, the smooth curves of trigonometric functions. The function mapping angles to their cosines cannot be written precisely as a combination of a finite number of linear pieces. But we can approximately represent cosine to any given degree of accuracy. More linear pieces means more precision. That's the essence of universality. Using this simple, regular program form, we can approximate any computation. The other powerful property of our otherwise boring neural network structure is learnability. The form of the program, line after line after line of maxes and weighted sums, is fixed in advance. The program itself is captured in the values of the weights W. Change the weights and we change what the program produces. If we randomly pick the values for the weights, the chance that the program does what we want seems pretty small. But we can look to see what it does, given those weights, and then go in and tweak them so the program does a better job. And that's what neural network training algorithms do. From a machine learning standpoint, the fixed architecture defines the representational space, while the setting of a network's weights defines a specific rule in that space. The loss function is then the sum over all of the examples in our training set D of the distance from the target output to the output produced by the program using our current weights. There are a bunch of ways to express distance mathematically. Here's a particularly nice one. We sum over all the input-output pairs, x, y, in our training set D. For each one, we put the input through the network with the weights set a particular way. We take the output that results from that computation and compare it to the target output y. The squared difference is a convenient measure of how close the two are. If they are the same, the value is 0. If they're close, it's small. If it's far, in either direction, it's a big value. Okay, so we have a representation, the weights, and a loss function, the squared errors. Now we need a way to find weights that produce a good score, capturing the desired computation. That's the job of the optimizer. A simple way to think about the optimization process is that we're going to iteratively shift each of the weights a little bit up or a little bit down, check the loss, and update the weights if the shift makes the loss improve. This approach is known as local search. Even in a network with just two weights, which we can depict as a point in 2 dimensions, there are a lot of directions the weights could be shifted that have the potential to improve the loss. In a network with thousands or millions of weights, finding a productive shift seems like finding a needle in a very high-dimensional haystack. Fortunately, there's a tool that answers the question, what weight shift most rapidly improves our loss score? It's precisely what differential calculus produces. The derivative of a one-dimensional function tells us the slope of that function, right? Well, the slope is telling us how much the function value increases if we take a small step to the right. This same concept applies to functions of many more dimensions, including loss functions. Because this quantity is a slope in higher dimensions, we call it the gradient, and moving down the gradient to minimize loss is gradient descent. What's the strategy at this point? Write the skeleton program. That's the neural network architecture whose components define the representational space. Guess values for the weights, which we can do just by assigning them small random values. Compute the gradient of the loss with respect to these weights. This high-dimensional slope gives us local information about how to decrease the loss. If the gradient ever reaches near 0, we have no more information about how to improve, so we should stop. Otherwise, if the gradient is non-zero, we can use it to move the weights in a direction opposite the direction of the current gradient in an effort to shrink the next round loss. We move the weights, then start the gradient computation process over again with this new set of weights. An important step I left out is how we compute the gradient over such a vast space of parameters. There is a procedure that first began to be more widely appreciated in 1986 called backpropagation, which is an algorithm that efficiently calculates all of the needed components of the gradient. Backpropagation works, as the name suggests, by running the program backwards and asking what sort of changes in the weights for each line would produce an output that the downstream lines could use to improve the score. We would have already run the program forward for all of the training examples, then we essentially run it again backwards on those same examples. At that point, we have the information we need to change the weights. Modern computer hardware and software libraries make this process fast and easy. To use a backpropagation approach to machine learning, you mainly need to choose the original program template, the data, and a few so-called hyperparameters for the search, like how far the weights should be shifted in each iteration. Then, the optimizer cranks away and finds the best weights it can. And that's neural networks in a nutshell. Let's take a look at how this idea plays out with an example in Python. We'll train a network to solve a perceptual problem, recognizing handwritten digits. We're using a famous dataset called MNIST. The name comes from the fact that the National Institute of Standards and Technology produced a modified version of an earlier digit database they had put together. Python's scikit-learn library includes a copy of MNIST. We can read it into an array of instances x and a vector of labels y. We'll randomly split 6,000 of the instances in this dataset into 5,000 digits for training and 1,000 other examples for testing what was learned. Xtrain and Ytrain are the instances and labels for training, and Xtest and Ytest are the instances for testing. An instance, in this case, is a vector of 784 integers, each between 0 and 255. Here's an example of one of these vectors and the corresponding label. I picked instance 417 arbitrarily. It says it belongs to class 7, though it's not yet obvious why. We could try learning a decision tree classifier based on this data as a baseline. I experimented with trees of various sizes and picked a big tree of 170 leaves. Smaller trees get significantly less good performance, and larger trees don't seem to get any better. Even so, 170 leaves is more than seems reasonable as an interpretable rule. Plus, the tests are also very difficult to interpret. And as we'll see, an accuracy of 78% isn't great for this dataset. Let's switch over to neural networks and see how that goes. First, it might be useful to see that these instance vectors of 783 integers can be analyzed visually. Here's the same instance vector from before. Now it's easier to see why the instance vector we looked at has the label 7. Okay, here's a purely linear neural network run on this same dataset. Training the neural network classifier in scikit-learn is very similar to training the decision tree classifier. The main difference is the use of MLP classifier replacing decision tree classifier when defining the classifier object CLF. MLP classifier means multi-layer perceptron, or a neural network. The MLP classifier function takes parameters that control the architecture and how it will be trained. Hidden layer sizes is an empty list because we're building a network with no hidden units. Activation is identity because we're using linear activation, which leaves the accumulated sum identical. MaxIter says we'll train for no more than 10,000 iterations. Even with no hidden units, this simplest possible neural network gets around 84 to 86% correct. Neural networks are very well suited to gathering low-level information from the entire input. The decision tree looked at only 170 of the pixels, but the neural network makes use of all 784 pixels. Our network architecture has one input node for each pixel in the image. It has 10 output nodes corresponding to the digits from 0 through 9. Let's upgrade to a neural network architecture with a layer of 170 hidden units using a ReLU activation function. I picked 170 because it looked like performance was peaking around 175, and I liked the idea of using the same constant that came out of the decision tree run. I trained it 10 times, and the results are interesting. It is doing solidly better than the training with no hidden units, peaking up around 91% accuracy. But there's a fair amount of variability from run to run. The non-linearity introduced by the ReLU activation makes the network more powerful, but also much more flaky. I also did some ReLU runs with fewer hidden units, and sometimes the performance was no better than chance with a problem with 10 classes, as it fell to 1 over 10 or 10%. Different runs give much more variable results with ReLU. You need to have enough hidden units in your neural network, otherwise the improved results you were expecting may not materialize. Neural networks are an approach to machine learning that allows for the combination of low-level features into higher and higher and higher level calculations. We can exploit almost the full power of computer programming, despite never even using a loop or an if-then statement in our network. Moreover, these apparently boring programs are universal, and they are fully differentiable. That is, unlike classical computer programs, we can use calculus to tell us the dependence of the weights, or parameters controlling the computation, on the correctness of the program they specify. The gradient of these weights tells the optimizer how they can be altered to improve the quality of the program. As we'll return to in later lessons, neural networks are being used to solve all sorts of cutting-edge problems, such as learning the meanings of words and recognizing 3D objects. But in the next lecture, I want to take you inside an especially simple neural network algorithm. That way, you can see and better understand for yourself how the machine learning process unfolds.